of electric field due to some shapes, 2D geometric and 3D geometric shapes. Now we have to come to the part of electric potential. Electric potential we can relate with the electric field like this, that electric field is the negative of gradient of V, where V is the electric potential. So basically, if E is a function of R, then we can then it can be written as minus dV dr. Okay, so if we want to find the x component of electric field, then we can write minus del V del x. I hat y component of electric field is minus j hat, and Ez equals to minus. Okay, so there are some properties of electric potential. First one is it is a scalar quantity, and it can also be defined as, okay, let us define the electrostatic potential energy first, and then we can define this with the help of electrostatic potential energy. Potential difference due to uniform electric field. Now we know V equals to E dot dr. Okay, from this thing we can write that V equals to E dot dr. That is of course del V, or dV we can write, because we are using the differential. If electric field is uniform, means it's not a function of R, then we can just write that dV equals to integration V1 to V2 R1 to R. Okay, yes, so V2 minus V1 equals to E into R2 minus R. Now a negative sign should be there. Okay, that means if this is a region of uniform electric field, yes, and if we take 3 points A, B and C here, and the distance between them is D, and the potential of this point is V, and potential of this point is V2, potential of this point is V3. Okay, then V2 minus V1 is equals to, sorry, V1 minus V2. Potential, there should be a potential drop in the direction of electric field. Okay, V1 minus V2 is equals to N into T. Similarly, V2 minus V3 equals to also E. Okay. So next concept is the electrostatic potential energy. This can be defined in two ways. One is self energy, which will be discussed in the Electrostatics-2, and another part is interaction energy. So what is interaction energy? Interaction energy is the energy required to assemble a system of charges from infinity to a finite distance between them. Okay. So if there is a system of charges like this with n number of charges, q1, q2, q3 dot dot dot. Let's say this is the ith charge and this is the jth charge, and the distance between rij is the distance between two charges. Okay. So interaction energy U is defined as K Q1 Q2 by Qi Qj. I am writing a general expression Qi Qj by Rij. Sorry, Rij. It will be sum for all I, j. Okay. Okay, so we have to take all possible distances. Okay. So this is the electrostatic potential energy. Okay, now at infinity we consider the electrostatic potential due to a point q. Let's say this is a point q and there is a point small q at infinity. We consider this point at infinity, the potential of this point is 0 at r equals to infinity. Okay, now we bring these charges into this area, into the region of electric field due to this charge. Now let's say distance is rij. Okay, so electrostatic potential is defined as this work done by these forces, by this external agent to bring this charge from infinity to this point. Okay, so what is the electrostatic potential? Let's say this is the point P. Vp equals to, for our test purpose, unit shall be of 1 coulomb. Okay, so Vp equals to what? Kq by r. This is r only. Okay, so this is just if this is we can write this as kq by r small q by q. So this can be also interaction energy of these two charges. This represents the interaction energy between two charges by the test charge. Okay, so when we are calculating the electric potential for the other at the point of the charge due to the other charge, then we have to divide by the test charge. Okay, and the charge situated at the reference point at the point which I am considering for my calculations, this is called the test charge. Okay. So this is the interaction energy between two charges. There is also motion of charged particles. So if we consider two charges 1 and 2 with the finite mass m, let's say m1 and m2, then the force on them, if I consider this as the system, then the F external is equals to 0 and hence linear momentum is conserved. Okay, and if there is no external electric field present here, let's say q1 and q2 are 2 points, then, and if we assume this as the system, then also the torque external is equals to 0. Okay, let's say this is connected by a massless rod. Torque external is also 0. The angular momentum is conserved. Why torque external is 0? Because there is no electric field. If there is electric field, torque external may not be 0. Okay. Yes, may not. External electric field can vary with the radius r. External electric field can be non-uniform in nature. Okay, so it may produce a force. It may exert a force in such a, yes. তখন তো ঠিক ঠিক সেটা একটা আচ্ছা, electric lines of force. So what is electric lines of force? This is another important concept. Let's say this is a charge, imaginary non-intersecting, forces which represents the direction of electric field. Now let us consider these two spheres. These are three-dimensional sphere here. Okay. Now let's say for this sphere there are n number of lines. Okay. So what is the electric field density for this electric field lines density for this sphere? Force lines of force. Let's say n number of lines of forces are there. So the density is equals to n by 4 pi r square, and this is equals to the electric field strength. Okay. So you can observe that electric field is proportional to 1 by r square is satisfied by this one. Okay, so electric lines of force represents the direction of electric field, and the density of electric lines of force, the density of electric lines of force, not inversely proportional, represent the electric field strength, magnitude, the magnitude of electric field strength. And I can just write in this. Okay, so this is electric lines of forces. Another important concept for this chapter is that you have to remember expression of potentials due to some geometric shapes. Okay, I think I can derive those expressions in another videos, and I will share with you. Okay, no problem. So next concept is what? Equipotential surface. So what is actually equipotential surface? Equipotential surface means, yes, you are correct, the potential is same at every point on the surface. Okay, now if potential is same, if we consider 2 points on equipotential surface, let's say this is A and this is B. Okay, and the distance between them is dr, let's say ds. Okay, so you can assume it like a line. Okay, straight line. Now if this is ds, then the change in potential Vb minus Va is equals to 0. That means E dot ds is equals to 0. That is E ds cos theta is equals to 0. Now E not equals to 0. E not equals to 0. ds not equals to 0. So cos theta equals to 0. That means theta equals to 90 degree. So it signifies that the electric field lines are perpendicular to the surface, to the equipotential surface, or yes, to the surface or equipotential surface, or perpendicular to the equipotential surface. Okay, so work done from moving a charge from this point A to B is 0 also. Okay, on moving a charge from A to B is okay, clear? ওয়ার্ক হচ্ছে না তো, মুভ হবে না। আমরা ইলেকট্রোস্ট্যাটিক্স যতক্ষণ পড়ছি ততক্ষণ অবধি চার্জের মুভমেন্টের কোনো গল্পই নেই। হ্যাঁ, so we can conclude this chapter with electric dipole, with the concept of electric dipole. What is actually dipole? A system of two equal and opposite charges. So electric dipole is basically a system of two equal and opposite charges. Okay, separated by a small distance. Okay, so if this is the negative charge and if this is the positive charge, then electric dipole is a vector quantity directed like this, and it is defined by P equals to Q into D. if this is equals to minus q and this is equals to plus q. Okay, so here we have to derive the expression for electric field, but I repeat, the derivation is not required for the revision purpose. Electric field at axial point. Okay, p vector by r cube, where r is the distance from the center. Okay, axial point means if this is the center and this is the, yes, let me tell, if this is the minus q and this one is the plus q and this one is the point r, then the direction is like, okay, at equatorial point where p is the dipole moment. Okay, so this is equatorial point. If these are two charges, one is minus q and another one is plus q, then at this point this is like this. Okay, where this distance is r and the magnitude of electric field is E equals to, okay, so what is the angle between P bar and P bar? Is 180. Okay, next thing is electric field at a general point due to the dipole. We can write in this way. Let's say this is a dipole. We can define two vectors here. One is like this, and another one is perpendicular to this. Okay, sorry, this would be at anti-clockwise direction. In anti-clockwise direction, like this. This is called r cap direction, and this is called theta cap direction. Okay, so E bar can be written as, if this angle is theta, then 2 kp cos theta by r cube r cap plus kp sin theta by r cube theta. Okay, so at an equatorial point, so this is the E r and this one is the E theta. At an equatorial point, theta is equals to 90 degree, so E r equals to 0 and E theta equals to kp by r cube. Okay, at an axial point, theta is equals to what? 0. So E theta equals to 0 and E r equals to 2 kp by r. Okay. Now, if this is the electric field, then we have to calculate the force. Force due to dipole. Okay, so how can we calculate force? Before calculating force, let me define the potential energy. Okay. So let's say this is a dipole and this is an external electric field E. So if this is minus Q and this is plus Q, then the force on this is QE and force on this will be QE like this. And if this angle is theta and the distance between them is D, then what is the torque? What is the torque? No, QE into D sine theta. So that is QE means P sine theta. So that is basically P cross E. Okay. So this is the torque. Now, for this case, if we want to rotate this, okay, we take this as if this is the torque, then work done to rotate d theta is what? Tau cross d theta, tau dot d theta, and tau d theta basically. Okay, what is tau d theta? That is Pe sine theta d theta. This is the work done. Now work done from theta 1 to theta 2. Work done to rotate from theta 1 to theta 2. That should be Pe. So this is that was the differential work done. Pe sine theta d theta integration from theta 1 to theta 2. So we can get like Pe cos theta 1 minus cos theta 2. Okay. So what is this? This is the change, and this can be, we can also define that work done rotate theta 1 to theta 2 in the presence of electric field is nothing but the u theta 2 minus u theta 1. What is u theta 2? This is the electrostatic potential energy at theta 2, and u theta 1 is what? Electrostatic potential energy. I'm just writing ESPE at theta 1. So we got u theta 2 minus u theta. So we can write u theta like this, Pe cos theta. Okay. No, sorry, u theta 2 minus u theta 1 is like that, Pe cos theta 1 minus cos theta 2. Okay, so that can be like this, Pe minus Pe cos theta 2 minus cos theta 1. Okay, so u theta 2 can be written as minus Pe cos theta 2. So u at theta can be written as minus Pe cos theta, that is minus P dot E. So force is what? Minus du dr, that is E dr. Okay, now if E proportional to 1 by r cube, then F is proportional to 1 by r to the power 4. Okay, or if E proportional to 1 by r square, then F proportional to what? So this is our discussion on electrostatic field part 1. Next we have to discuss the electrostatics 2. Now in electrostatic 1 we just learned. So in electrostatic 1 part that I skipped is that one part that I skipped is that I have not calculated the electrostatic potential, sorry. due to various charge distribution, due to different kind of charge distribution. Okay, but this was important. Okay, I will provide some videos. I will upload some video in YouTube and I will share with you. Okay. So next, in electrostatics 2, we have to learn about electric flux. What is electric flux? This is the group of field lines. Okay. Numerically, it is defined as V dot ds. If this is a differential area, okay, sorry for the interruption. So if this is the ds like this, and some electric flux lines are passing through the area like this, if this angle is theta, okay, so that can be E ds cos theta. So ds cos theta is what? Is the area vector, area perpendicular to the, not area vector, area perpendicular to the flux. Okay. Okay. So from this thing we can write that E is basically phi by S perpendicular. S perpendicular has been defined in this way. Okay. Okay. Next, we need to develop another mathematical concept. This is the concept of solid angle. So this is the extended version of concept of 2D angle. Okay. And it's a kind of 3D angle. Okay. So 3D angle means it is just the angle enclosed by this lateral surface of a cone. Okay. How 2D angle was defined? The angle enclosed by these two lines, these two radius of the circle. If this was the S, this was the R, this radius of the circle is R, this is the theta, then S is equals to R theta. And here we can define like this. If this is the S perpendicular, okay, then S perpendicular equals to omega r square. Okay. Okay. Now let us do some mathematics on that. Oh, sorry. So that should be x d phi. This width should be what? X time d phi. Okay. And what should be the area? 2 pi r. Where r is this distance. Now the problem is 2 pi. Okay, so let me rewrite these things. Okay, so for this case width equals to r d theta, capital R d theta. and the area is equals to what? 2 pi small r into capital R d theta. And small r by capital R equals to sin theta. So small r equals to capital R sin theta. So this can be represented as 2 sin square theta d theta. So what is the total area? This is integration 2 pi r square sin theta d theta 0 to pi. Pi is the half angle. Okay. So 2 pi r square cos theta 1 minus cos phi. Okay. So this is the total area. That is equals to omega into r square. Omega is what? 2 pi into 1 minus cos phi. So this derivation is so simple. Okay. So this is the concept of solid angle. Now, if phi, if this phi equals to equals to pi, okay, then what should be the omega? Omega should be 2 pi 1 minus or minus 1. That is equals to what? 4 pi. And phi equals to pi means what? 2 phi equals to 2 pi. That means this total circle. Okay. So this is just a sphere. Okay. So this is the concept of solid angle.